This video is about resonance forms and how we can see those from Lewis structures. So what resonance forms are, they're Lewis structures that differ only in the location of electrons. And the best way to illustrate this is just to draw some for you. So let's draw the Lewis structure for the carbonate polyatomic ion, CO3 2-. So first step is count up the number of valence electrons and check my work, make sure we get the same number. Don't just trust me, count them. I think there's 24 electrons, and when we arrange the atoms, because carbon is less electronegative than oxygen, we put that in the center. And so this is the arrangement that we get. It doesn't matter if you put an oxygen up top instead of the bottom or anything different than this. Just try to arrange them symmetrically. Next, we connect the outer atoms to the central atom with single bonds. Each bond represents 2 electrons, so that's 2, 4, 6 electrons we've used up, leaving behind 18 valence electrons we still want to use. Our next step is to satisfy the octet rule for the outer atoms. Each of the oxygens in this structure here only sees 2 valence electrons. It needs a total of 8 for the octet rule, and so each of these oxygens needs 6 more. And so we put those in as dots, lone pairs of electrons, and that's 6, 12, 18 that we've used up. Now, we've used up all of our valence electrons. We don't have any more left, but carbon still does not have its octet rule satisfied. See, it only sees 2, 4, 6. So this is a step where we need to make a double or maybe triple bond. So again, what we do is we look for an atom that's attached directly to the electron deficient atom, in this case to the carbon, that has 1 or more lone pairs of electrons. Well, there's tons of them, right? Each of these oxygens has 3 lone pairs. So just pick one. Now here's the thing. When you get to that point where you have a choice as to where you can take your electrons from, that means that you're going to have resonance forms. So let's pick this one. Just randomly pick the one on the left. It doesn't matter. We could have picked any of the other ones. And that's kind of the point. When we do, we take those 2 electrons that were here, make them into a bond. Now this is a double bond here. And so this oxygen still sees 2, 4, 6, 8 valence electrons. Everybody else sees 8. So that's a good Lewis structure. We put the brackets around it because it has a charge, and we put the charge outside. Now, because we had the choice, we chose to take these 2 electrons here. We could have taken them from here or here, right? And so that means we had resonance forms. So this is a resonance form of the carbonate polyatomic ion. This is what it would look like if we had taken the electrons from here. And the other one looks like this if we had taken the 2 electrons from here. Notice every time we make a double bond, that second line, we had to erase 2 dots. That's important. So we now see that the carbonate polyatomic ion has 3 resonance forms. What that means, okay, is that first of all, the carbonate ion only has one structure. The real structure, it's like an average of these forms. So, the kind of questions I might ask you would be, how many resonance forms are there for the carbonate polyatomic ion? The answer would be 3. Now, here's the thing. For that question there, listen, write this down, okay? If the question is, how many resonance forms are there for some molecule? The answer is either 0, 2, 3, or some higher number. It's never 1, because if there's no resonance forms, then it's 0. If there's just one structure, there are 0 resonance forms. Then the next possibility is if there are 2 structures. Well, they're both resonance forms, so that means there's 2 resonance forms. All right, so let's do one more example, the azide ion, N3 with a negative charge. So each nitrogen has 5 times 3 is 15, plus 1 is 16 valence electrons. We arrange them, doesn't matter, they're all nitrogen in a row. Next step, when we connect the atoms, we use up 4 of their valence electrons, leaving behind 12. Next step, satisfying the octet rule for the outer atoms gives us this. We've used up all of our 12 electrons. The 2 outside atoms have their octet satisfied, but the central nitrogen, it only sees 4 valence electrons. It needs 4 more. So we have to make multiple bonds. Now there's several possibilities here. One, we could take 2 lone pairs from this nitrogen and make a triple bond here. We could take 2 lone pairs from this nitrogen and make a triple bond here. Or we could take 1 lone pair from this nitrogen and make a double bond, and 1 lone pair from this nitrogen and make a double bond. We have 3 possibilities. They're all equally good. That tells us there are 3 resonance forms. And here's what they look like. This is if we take 2 lone pairs from the right nitrogen and make a triple bond. See, this nitrogen now sees 2, 4, 6, 8. This still sees 2, 4, 6, 8. And this sees 2, 4, 6, 8. Or we could have taken 2 lone pairs from the left nitrogen, made a triple bond here. Or we could have taken 1 lone pair from the left, make a double bond, 1 lone pair from the right, make a double bond. And so there are 3 equivalent resonance forms for the azide ion, N3-.